Okay. Interesting example which we discussed it. Okay. Now, let us come to the other applications of mean value theorem. So, first is the Rolle's theorem. With the help of Rolle's theorem, one can find the location of roots of a function For example, if a function the reason is because if a function g can be identified as the derivative of another function f, then between any two roots of f, there is at least one root of g, because what the Rolle's theorem says, if a function f g between any two roots of f j. Okay. If a function f such that f of this is interval a b, f of a equal to say f of b, this is b. Okay. This is b. So, this is the function f. If the function f is a continuous over the closed interval a b and differentiable over the open interval a b, and at the point a both f a and f b is 0, then there exists a point c in between where the derivative of the function f prime c is 0. It means, if I say g is a function which is equivalent to its derivative, so between any two roots of a b function f, there is a root of g, because this is equivalent to g c. So, that is what. For example, if we look the function f x, which is say sin x, okay, then let alpha and beta be the two roots of this function sin x. The sin over the interval, say any interval I take, say between the interval say minus say a to b, just a to b. Okay. Or let us take the exact root, because this sin becomes 0 is 0, sin pi is 0. So, between minus say over the interval minus pi by 2 to pi by 2. Let us take this interval. Okay. Pi by 2 minus pi by 2, it will not help, because one will be 0, other net. So, do not take it. Let us take the interval say minus pi to pi. Let us take this interval. Okay. So, this is the function sin 0 is 0, sin pi, then minus pi. So, pi. So, the function f is such which is continuous and differentiable over this interval. Now, there exists at least one root. Obviously, this is one of the point where the derivative vanishes, and here this is another point where the derivative vanishes. So, what is the derivative f prime x? The f prime x is cos x. So, cos x vanishes at the pi by 2 and then minus pi by 2. So, it shows that between any two roots of the sin x, there is a root of cos x, and vice versa also. If I start with cos x, then its derivative is sin x minus sin x of 4, then again between any two roots of cos x, there is a root of sin. So, one can locate the roots of the function with the help of Roche theorem. The second, we can also use the mean value theorem to approximate or for the approximation of the roots, for the approximation of some say approximate calculation, you can say for approximate calculation. Let us see how. Suppose we wanted to find, to evaluate this, evaluate under root say 105. Okay. Now, if I look this, take the interval suppose 100 to 105, okay, and the function f x if I take to root x, then apply the Lagrange's mean value theorem. Mean value theorem. What we get is f of 105 minus f of 100 is equal to the derivative of this function at some point c into the length of the interval 105 minus 100. 105 minus 100, where c lies between 100 and 105, where c is this. So, what is this? This is equal to 105 minus 100, this is equal to 1 by 2 root c into 5. So, 5 by root 2. We can approximate roots 2 now. So, since our c lies between 100 and 105, so root c will lies between 10 and under root 105. This is almost approximately or less than say 11, less than 11. Okay. So, it means this value. So, what we get, therefore, under root 5 105 minus 10 will lie between these two bond. The bond will be 5 over 2 into 11 and 5 over 2 into 10. Okay. Therefore, the root 105 will lie between this 10 plus 5 by 22 and less than 10, this is 10. So, minus 10 here, because this will go from here and this will come. So, 105 with this and this minus say 10 plus both sides. So, this is 10 only, and then it will be 5 over 10 plus 5 over 20. Now, this is an approximate value for this. So, one can get the value accordingly. Okay. So, this is another application of this. Then inequalities can also be established with the help of this. The inequalities, suppose I want to establish so that e to the power say x is always be greater than equal to 1 plus x for x belongs to R. Okay. Now, we know that e to the power x is always be greater than is positive quantity, is always be positive quantity when x belongs to R. Is it not? Work 1 plus x, or if x is negative 1 by x, and its derivatives, and its derivative f prime x is e to the power x itself. So, f prime x will always be greater than 1 when x is greater than 0 and is less than 1 if x is less than 0, because it is 1 upon e to the power x, and for the x equal to 0 it is 1. Okay. So, 1 occurs if 1, clear. So, this will be the solution for. Now, to establish this result, consider the interval, say we take the interval 0 and x, this closed interval, and choose the f x as e to the power x. Now, this function is continuous, differentiable in the interval inside the interval 0 x. So, by the mean value theorem, Lagrange's mean value theorem, the value of the function at the end point is equal to the derivative of the function x at the point x equal to c into the length of the interval x c. So, we get what? E to the power x minus 1 is equal to e to the power c into x, where c lies between what? C lies between 0 and x. C is greater than 0. So, e to the power c will be greater than 1. So, it is greater than or equal to x. At the most 0, when c is equal to 0, it is 1. So, it is x. So, this shows e to the power x is greater than or equal to 1 plus x for every x belongs to R positive. Now, similarly, we can show for x belongs to R negative, it is true, greater than or equal to this. Hence, for all R it is 2. So, this can be shown. So, this also inequality we can use it, mean value theorem. Now, there are certain Daleks theorem being required, the Daleks. Okay. So, in order to prove the Daleks theorem, we first need this lemma. Proof we can skip because it's proof. Let R I, which is subset of R, be an interval, and let f is a mapping from I to R. Let C is a point in I, and assume that f has a derivative at C. Then this lemma says, if derivative of a function at the point C is strictly greater than 0, then there is a number delta greater than 0 such that f of x is greater than f of c for x belonging to I, such that it lies in the right hand side of the interval of the neighborhood of C, and if f prime x c is negative, then there is a number delta greater than 0 such that f of x will be greater than f c for x belongs to I, such that c minus delta less than x less than c. So, what this it says is, suppose f is a function and c I is an interval, c is a point belonging to this, and function has a derivative at this point. Now, if the derivative is strictly greater than 0, then what it says is, we can always find a right hand side neighborhood of this C, where the function will have a positive value, where the function f x will be always be greater than the value at the point C. So, here in this interval, the function f x will always exceed the value at the point C. It means that f of c will behave at the lowest point in this interval if derivative is positive, and if this f of x is and if derivative is negative, then in the left hand side of this neighborhood the value of the function will always be positive if here. So, here if the derivative is negative at the point C, if the derivative at a point C is negative, then we can get this in neighborhood left hand where the function is exceeding the value f c. If derivative comes out to be positive at the point C, then we get the right hand side interval where the functional value exceeds the value at the point C. So, using this lemma we can prove the Daleks result. In fact, the proof of this is very simple. Since the derivative exists, since this derivative f prime c exists, which is the limit of this f x minus f c over x minus c, this exists and it is given to be say greater than 0. Now, when the limit greater than 0 x tends to c, then obviously this entire thing must be positive. So, this is only possible when limit is strictly greater than 0. It is only possible when this quotient should be greater than 0. Otherwise, if it is negative, we cannot get the limit to be strictly greater than 0. But x is, if I choose x in the interval for so there exists in this is greater than 0 in some neighborhood 0 less than x less than mod x minus c less than delta. Okay. So, means there exists if it is greater than 0, then there exists a delta greater than 0 such that if x belongs to I interval and 0 less than mod x minus c less than delta, then this holds. Okay. So, if x satisfy the condition, if x belongs to I and satisfy the condition x is greater than c, then from here we get implies. So, f x must be greater than f of c, otherwise this will be negative. So, that proves the result for the first part, similarly for the other. Okay. So, this we can see. Now, Daleks theorem, which is Daleks theorem. Basically, what is the Daleks theorem is? It states that if a function f is differentiable, function f is differentiable at every point of an interval say I, then the function f prime, that is the derivative of this function f prime, has the intermediate value, has the intermediate value property. It means, that is the meaning of this is, that is if f dash takes on values a and b, then if it also takes on all values between a and b. A and B. Okay. So, this is our exact statement is we can see exact statement is if f is differentiable on the interval I, as closed and bounded interval I, and if k is a number, between f prime a and f prime b, then there is at least one point C in the interval a b such that the derivative of the function at the c is k. It means, if f is differentiable throughout this, means derivative of the function exists including the derivative at the end points. Then if I picked up any arbitrary number which lies between f dash a and f dash b, then there will be some point where the derivative of the function at that point will coincide the numbers k. So, it can attain all the values in between a and b, which is taken by this. Okay. So, means the maximum and minimum value. Okay. So, proof is like this. Suppose that k lies between, suppose k lies between f prime a and f prime b. Okay. Now, we define the function g on I by g x equal to k x minus f x for x belonging to I. Let us define this. Now, since function f is continuous and differentiable, so g is also continuous and differentiable. So, since f is continuous on the closed and bounded interval, this is closed and bounded interval. So, this shows g is also continuous on the closed and bounded interval. So, if it is continuous on a closed and bounded interval, then it will attain its maximum value on the interval. Then g will attain its maximum value, similarly minimum value also, maximum or minimum value, maximum and minimum value of course, on I. So, here we require the maximum and minimum when this is less than. Okay. So, we get this I. Now, since our derivative g prime a, that is by definition is coming to be what? K minus f prime a, this is by just differentiated, and this g prime a is positive. Why? Because our choosing k lies between f prime a and f prime b. So, this is positive, this is positive. Now, it follows from the previous lemma. So, by the previous lemma, what it says, if the derivative is positive, then there will be a one neighborhood, is it not? So, if the derivative is positive, then there is a number delta such that in the right hand side of this neighborhood, the function f x will be greater than this. So, we get from the previous lemma, we can say that the maximum of g there exists a right hand side neighborhood, say a to a, we can say a to a plus delta, such that the derivative, the functional value g of x, g of x is greater than g of a. Therefore, the function g cannot attain the maximum value at the point a. So, therefore, the maximum value of g does not occur at the point x equal to a, because it already violate. If it is maximum, it must be g x must be less than or equal to g a, which is not true, not occur. Similarly, since g dash of b that is equal to k minus f prime b is negative. So, again by previous lemma, again there is a left hand side where the value will be greater than the less than this. So, again this shows that g by the previous lemma, that maximum does not occur, that maximum does not occur at x equal to b. So, neither it occurs at x equal to a nor at x equal to b. Therefore, but maximum should be attained because it is continuous over the closed and bounded interval. Therefore, g will attain G attains its maximum value maximum at some interval at some point C which lies in the interval a b. Okay. Now, again a function g is such which has a derivative and maximum is attained at some point. So, according to the theorem, according to previous we have discussed is according to the theorems earlier we have seen that there exists a point we have 0 which is less than equal to g dash c, which is k minus f prime c, and hence f prime c is k. According to the theorem, this theorem I am putting a star, and this star is we can say this theorem is there. The theorem says which is interior theorem is that let C be an interior point of the interval I, a interior point, and then at which the function has a relative extrema, at which f has relative extremum. Then if the derivative of the function at this point C exists, then the value of this must be 0. This was the result which we have already proved. So, using this result we get this. Therefore, this complete. Okay. So, thank you very much. We have not covered the L splitters. Next lecture we will do it. Thank you very much.